Normally B value is far lower. I have already told you that normally B has a value of 1% to 3%, at the max to up to 10%. So if I consider 1%, it is going to be 0.01 normally. On the other hand, R, as I told you, this is speed governor regulation, isn't it? This is speed governor regulation. This will be somewhere around 3 to 5. So normally 1 by R will be somewhere around 1 by 3 to 1 by 5, which will be somewhere around 0.33 to 0.6. Sorry, 0.2. So when compared to this one, you can see that B value is very, very low. Yeah. So neglecting B over 1 by R. So this will result in delta f of s steady state value is equal to, now in this equation I'm going to neglect B value. So I'm going to get this is 1 by R, right? Delta PC of S, sorry, delta PC minus delta PD. Okay. Now, looking back. Now, if you can see, delta f of s is equal to R into delta PC minus delta PD. During free governor operation, so delta f of s is equal to minus R into delta PD. This is a change in demand. This is a change in frequency. So how will it be? Basically, if this is delta PD, if the demand is varying, so automatically the frequency will also be varying, but see the slope is going to be minus R. So it will be like this. Okay. The slope is R. Okay. The slope is so now let's look back. So I hope now you have understood what is a steady state operation, how steady state values of frequency will be determined. Now we will move ahead with dynamic response. Before moving into the dynamic response, I would like to state one thing. For delta f of s to be 0, if I need delta f of s to be 0, for delta f of s to be 0, what should I do? Delta PC minus delta PD must be 0. So in order to get this one, what I should do, this is the condition which I am supposed to maintain. Whatever the demand change is there, I must manually change the speed changer setting so that the generation has increased. So this rule is to be followed if you want no change in the frequency. Okay. Now, having said that, moving on to dynamic response now. This is dynamic response. We have already derived the transfer functions, and now we are going to look into a detailed system thing. Considering overall transfer function, of single area system of the single area system, you can see I have if you can carefully see, this is a third order system, isn't it? So this is considering overall transfer function of the single area system. It is generally the third order system. It is generally the third order system. As already I mentioned to you, the typical time constants. How many time constants you do have? You do have three components. Three components are there, so you will be having three time constants. One is time constant of the speed governor, time constant of the turbine, time constant of the generator, load module. So typical time constants are such that speed governor is a lighter one when compared to the turbine, which is very lighter when compared to your PS. So this is not equal, this is far. Okay. So normally what I'll be taking is I'm taking this one as 0.4 seconds, and I'm taking this one as 0.5 seconds, and I'll take it as somewhere around 20 to 100 seconds. So I'm taking some random rough value of 20 seconds. So these are the typical time constants. Also, assuming Kg into Kt is approximately equal to 1, which we have already considered in our steady state analysis also. And if you carefully see, if you consider these time constants, tau Sg is somewhat equal to tau T, which is far less when compared to your tau Ps. So neglecting tau Sg and tau T. So I'm gonna neglect tau Sg and tau T now. Okay. So let's see how it is gonna happen. So I'm again redrawing the entire circuit. I will start from the first one. Right. This is your model of the system, single area system. Now, if you can carefully see what I'm gonna do, I'm neglecting this time constant, I'm neglecting this time constant. So this will become 0, this will become 0. So what I'll be getting? Ksg by 1, this is Ksg, this is Kt by 1, this is Kt. Again, if I multiply these two, I have already taken assumption that Ksg and Kt multiplied will result in 1. Okay. So, which means that I'm not going to consider these two now. So, now, assuming free governor operation, I'm going to consider free governor operation, which means delta PC is equal to 0. So now let us see delta f of s at the condition that delta PC is equal to 0. So what will happen? We have done it already. So this will become 0. So this is the entire feedback now to this system, isn't it? This is going to act as a negative feedback to the system. And this is going to be G, this is going to be H for you. So the input is only one input. I do have delta PC of S, that to negative value, delta PC of S. Now this is going to act as a negative feedback. See, this is negative feedback. This is a forward transfer function. So KPS by 1 plus S into tau PS. This is forward transfer function. 1 plus feedback is 1 by R into KPS by 1 plus S into tau PS. Okay. This is the model. This is the overall transfer function. Yeah. Sorry, this is PD lines. This is PD. This is electricity demand. This is PD. Okay. Now, considering change in demand is constant. Demand is not constant. Change in demand is constant, which means that there is a fixed value. Delta PD of time is going to be some normal value. I'm considering it as delta PD only. This is some X or Y or some other value. This is some constant value. So if I apply it to Laplace transform, this will become into 1 by S. Okay. So now I'm going to substitute this one here and I'm going to simplify this one. So what I'll be getting now? Isn't it? This is my transfer function. If you see this minus, I'll be getting it out. Okay. This is KPS by S into so I'm gonna take this one out, tau PS. So this will become okay. This is S into S plus A type concept. Okay. So I hope you do remember this sort of a Laplace transform. I'm gonna simplify this. I hope you are able to see. This is delta f of s is equal to minus, yeah, this one, right? Minus kps by tau ps by s into s plus r plus kps by r into tau ps. This is some constant value. Okay. Now, I think you know these things, how you will be solving. Okay, consider, I'm taking a random function for you. Consider some a by s into s plus b. Okay, so what you'll be doing these sort of things, this is going to be a1 by s plus a2 by s plus b, isn't it? So what you'll be getting here? Anybody? Any idea? So this is going to be let me do the things, simplification for you. This is a is equal to a1 into s plus b, this is a2 into s. So this model is going to give you an output of, this is a by b by s minus a by b by s plus b. See, what is a value here? This is a value, isn't it? What is b value here? This is b value. Okay. So now I'm gonna consider this one, delta f of s is equal to, so I'll take a by b as common. Okay, this will give 1 by s minus 1 by s plus b. So minus a by b, a is kps by 2ps by, this one is r plus kps by r into 2ps. This is a by b, isn't it? Into 1 by s minus 1 by s plus into delta PV, isn't it? So I'll take this one as r into kps by r plus kps into 1 by s minus 1 by s plus. Don't feel that I'm doing lots of calculations. Once we do all these things, we will get a practice about control systems and also networks and mathematics. That's why I'm doing again and again every year. So applying inverse Laplace. So dynamic response is all about converting the entire thing into time domain. Okay. Now let r into kps by r plus kps is some sort of alpha, and I'm considering this one as so what is this one actually? Delta f of s is equal to minus alpha into 1 by s minus 1 by s plus beta, right? So if I convert it into time, this is f of t, this is minus alpha. For 1 by s, what is the Laplace integral beta? 1 minus 1 by s plus beta. What is the Laplace integral? E to power of minus beta t, isn't it? So this is going to be your response of the system. 1 minus e to the power of minus beta t. Okay. How this response will be? So I'm going to show you. This is f of t minus alpha 1 minus e to the power of minus beta t delta pt. So this is going to be just like here. We have taken so many approximations. So normally this is 1 minus e to the power of minus t function. So how will it be? If I consider it in time seconds, so delta f will be this is 1 minus e to the power of minus t, right? So this will be this is going to be minus alpha. This is the value. This is approximated curve. Okay. This is approximated curve. Okay. Now this settling time, as already we have discussed, this is going to be somewhere around 5 beta. Okay. 5 times the time constant, because the time constant is beta here. So this will be sometimes around 5 beta or 5 by beta. Okay. Now this is an approximated curve because we have taken so many approximations. K, Z, and K's into Kt is equal to 1. Like that, we have taken so many approximations. But ideally, the curve will be like this. I'll draw it with a pencil. Ideally, the curve will be like this. I'm not a good artist, so it will be oscillating. Okay, this is going to be the curve. This is the actual curve. So it will be going down and up and down and before finally settling down to the same value. Okay, this is the actual curve. This is our approximated curve. Okay, this is what is called as a dynamic response of the system. Okay, this is called as dynamic response of the system. Dynamic response is nothing but determining or understanding what is the variation of any variable with respect to time. Okay, dynamic is with respect to time. Thank you for joining, guys. Hope we have discussed the steady state response and also the dynamic response of single area system. In the next class, we will go through the two area system. Okay, that's it for today. Thank you once again.